Hi everyone. This time I'm going to talk a little bit about EV charging and the issues surrounding that. Full disclosure, I do have an EV right now, and in the past I've operated gasoline engine vehicles, uh, hybrids, as well as natural gas cars. I do have an interest in energy technology and power and so on. One of the previous technologies was natural gas and talk about hydrogen as well, but based on my experience with natural gas, I think the capacity and the infrastructure for natural gas was pretty poor, and I assume it will get the same problem with hydrogen as well, which requires more higher pressures and so on, and leakage issues, etc. Anyway, one of the things with electricity is that it's widely available. Most homes have at least in the US, have a 120 volt and a 240 volt connection. And so that makes it somewhat easy to do overnight charging using electricity. So unlike the gas, which everybody doesn't have, and also the pressures required for gas to charge natural gas vehicles. Um, the biggest hurdle to EV adoption is probably on the long distance driving aspect. That's where the DC fast chargers technology comes in, where you need very high power that can charge a car rapidly within 10 minutes or an hour or in that range of time. If it becomes much slower than that, as adoption is going to be slow and have a lot of resistance. So anyway, let's get into this topic a little bit, and first go into the power requirements, especially and compare that with what an average home uses, and then translate that to the EV charging infrastructure itself. So if you look at a typical home in the US, there are a lot of appliances that use electricity. I'm only talking about electricity here, and this list over here will change depending on a lot of things, such as you may have an electric stove and you may not have a electric clothes dryer, but a gas clothes dryer, and you may not have an AC, or you may have an AC. The water heater could be gas, could be electric. So these are numbers that approximate and in general reasonable, I think. So let's look at the total power of all these appliances I've shown here: the washing machine, the clothes dryer, refrigerator, a 2-ton central AC, a water heater, and some miscellaneous stuff. So the total works out to about 16 kilowatts. So kilowatts is the power requirement. It's not an energy requirement. So if you integrate, that is, add up all the power over a certain period of time, you get the energy that is consumed. And one of the things to note with electrical power or electrical motors is that they require a surge current when they start up, and so typically you have to account for that. And so the total starting power, if all these appliances were turned on at the same time, you would need about 25 kilowatts to do that. But that's not usually the case. These are operating in a asynchronous and staggered manner, so typically you won't ever reach that kind of power level. Now, if you look at the total energy, which is, as I said, the integration of power over time, uh, that's about 900 kilowatt hours per month in a typical average US household. That works out to about 10.8 megawatt hours per year. That number varies depending on the geographical location of the home. In warmer climates, you have more AC requirements. In colder climates, you have more heating. And some of the more temperate regions like California, parts of the east, you may have less of the power requirements. So if you take the average power of this 900 kilowatt hours, average it over a 24-hour period over 30 days, that works out to a total or an average power consumption of 1.25 kilowatts continuous. So that's something, a number to keep in mind as I get into the EV issue. So a couple of notes about DC fast chargers. Now at home you're going to have AC charging at either 120 volts or 240 volts. That makes a huge difference when you go from 120 to 240, as the power delivered is proportional to the square of the voltage. So you can get up to 4 times faster charging with AC powered at 240 volts at home. Uh, that makes it fairly practical for overnight charging of most vehicles. Now, in the DC fast charging, you are typically using them when you're traveling between cities or longer distances, and the typical state-of-the-art chargers now go from anywhere on the low end from 20 kilowatts all the way up to 350 kilowatts. So this is again power and not energy. So one has to bear that in mind, and I will go into that in the next few slides about the differences and how it's calculated. And the DC voltages which are typically available from these chargers vary from 150 volts all the way up to 920 volts. I believe these are not the Tesla chargers, which I think currently operate around 400 volts DC. But I believe the newer chargers from the other manufacturers in Europe and others countries do support or are going into the 920 volt or maybe even a kilovolt. So as I mentioned earlier, practical charging times is very important for mass adoption of EVs, and that typically will vary from a few minutes, tens of minutes maybe, to an hour. If it's longer, it's unlikely to have a great adoption because people don't want to stop every hour. I mean, for an hour or longer to charge their car, and which adds significantly to the trip time. So let's look at one of the typical EVs that you find commonly on the roads these days. Its range is about 300 miles, and typically an average decent EV will consume about 250 watt hours per mile. It could be a little bit lot more than that, like 300 or 350, but a fairly efficient one is about 250. A very efficient one would be probably in the neighborhood of 200 watt hours per mile. It's not going to get much lower than that due to the physics of moving that amount of mass and other weights involved and also the momentum issues and so on to start and to get the EV moving. Anyhow, so this average number is fairly representative. So based on the mileage, range, and the energy use, you can calculate the battery energy at 75 kilowatt hours, usable that is. Now the fields that are marked in shaded with light orange or pink are the user inputted fields, and I assume that a charging of 80%, that is from 10% to 90%, is what would be a full charge. Beyond that, it's going to take a very long time because the way the chargers work. So the energy requirement is based on the 80% charge is going to be 60 kilowatt hours. If you charge for half an hour, then the average kilowatts that is required over this half an hour period would be 120 kilowatts sustained. That is, but the chargers never operate in a constant power mode. You'll have to see why soon. And if typically, if you for these kind of cars, the typical voltage right now available is 400 volts DC, which works out to 300 amps of current, which is a huge amount of current actually. You've got special switch gear and so on to connect and disconnect these kind of currents, especially for DC. Now, based on the power requirement from the previous slide, this kind of a single charger will power 7 homes at full capacity, like at 16 kilowatts or so. Now, the charging profile is on the right. If you look at the bottom graph, that shows the power as a function of time. In the beginning, when the battery is depleted, its cell voltages are fairly low, and so the amount of power that can be delivered depends on the difference in voltage between the charging voltage and the battery voltage, with some uh, caveats involved there with regards to amount of current that they can accept and the temperature and so on. So on a perfectly well maintained battery with ideal temperatures, this profile would require an initial charging of about 190 kilowatts or so, and then it will taper off as the battery starts to charge, because the amount of voltage that builds up on the battery will resist the amount of current that can flow, because the current is basically V over R, and the internal battery resistance will start to increase, or the difference in voltage will start to decrease, which causes the current to drop off, and then you want to prevent the heating of the battery, so you want to taper off the charge gradually as it approaches full charge. And this is mostly true for any type of battery technology. I don't know how the solid state batteries would perform under these conditions, but in general the power will drop off because of the voltage difference and also some of the heating effects causing the resistance in the cells to go up. So this is very practical. As you can see, it takes 30 minutes and the power, and this is what you will normally see in a DC fast charger in most cars operating today. So recently another car company announced EV that has a 900-mile range and a charging time of 10 minutes. So I wanted to look at the feasibility and what kind of power requirements would be necessary from this kind of a DC fast charger, assuming similar charging profiles. So with a 900-mile range and very similar uh, energy level use, because it's going to be again a big car for that kind of range and battery size. So assuming it's as efficient as the previous car in terms of energy use, it's 250 watt hours per mile. So the battery energy required would be 225 kilowatt hours. It's a pretty huge battery. But assume the battery fits and everything else is good, and the same 80% charging, which probably is not needed, but I'm just saying if you want to, the company claims full charge of 80% or something in that neighborhood in 10 minutes. So the energy that requires to be supplied to the battery is 180 kilowatt hours in 0.17 hours, which is 10 minutes. So the average kilowatts that's required over this time would be 1.06 megawatts. That's a huge amount of power. I mean, that can power 64 homes uh, at a given time. So if you have like five cars charging at this rate, you would have the capacity to power almost 320 homes. That's a lot of power, and we are not sure whether how the grid can support that kind of power. Something to be aware of. Now the current requirement would be at this even conservative 1 kilovolt of voltage would require 1000 amps, 1060 amps almost. That's a tree trunk of a cable, really. I mean, that's require very special switchgear to handle that kind of current. Unless they go to much higher voltages, we haven't seen those yet. So that's another area to be aware of where they go with the voltages. So the average power is, as I said, 1 megawatt, and that translates to 1 kiloamp, and that's average. Now, if you look at the charging profile, you would need a much higher uh, power delivered in the beginning for the first 4 to 10 minutes or so. And sorry, 4 to 6 minutes, and then it starts to taper off. That power requirement would be 60% higher, as you can see from this graph, and that would mean at the same voltage of 1.6 kiloamps. Now this is something that I don't know how that's going to be delivered. Something to think about, I think, whether this is really feasible, how does that affect the grid, and how does that translate into a number of cars that can be charged simultaneously at a charging station for an EV like this. So to conclude, this video is likely to ruffle some feathers on both sides of the EV fence, but I just wanted to present some ideas and numbers that seem realistic to me, and hopefully this will spur some movement, at least in getting the EV charging issue more into the open. There are a lot of challenges, especially in the last mile or so of these charging stations and so on, and how they're going to be built up and so on across the country. So hopefully this was useful and informative. Look forward to your comments below, and this is not a topic that's to be gone anytime soon. See you next time.